Hey everyone, welcome back to Power Electronics. Today I wanted to fulfill my promise of doing a DAB tutorial, right? Going through the design of a DAB converter and selecting some specific parameters in the converter. So I put together a little problem, just threw some numbers together, and then let's just walk through it, see what happens. Okay, starting off, should probably begin with the given variables, right? So what I've provided is an input voltage, VG, equal to 48 volts. And we have a desired output voltage of 5 volts, right? So this is a 48 to 5 converter. Our output current is going to range from 10 amps all the way down to 1 amp, right? And this is basically going to determine our range of phase shift. I've provided a switching frequency. We're just assuming that this converter is going to operate at 200 kilohertz. However, this is actually another variable, and typically when you're designing this, you want to choose, the optimal switching frequency. So maybe there's some limit on, the size of your inductor, or there's some limit on how quickly you can switch, the fastest switching frequency you have, or maybe there's a limit on how much switching loss you can have, or total loss. That might determine what your switching frequency is. However, here we're just going to assume that it's 200 kilohertz. And finally, we have a constraint on the maximum output voltage ripple, right? So this is what I'm describing here is the average to the peak, right? So the middle to the top, or the middle to the bottom. And we're going to say that this is 1% of the output voltage, which is 50 millivolts. And then what this translates to in terms of the peak to peak, so we say 2 delta V out, that is 100 millivolts. So this is basically going to help us determine what the output capacitor should be. So specifically, with the DAB, we have these parameters that were given, and what we want to find is the following. So first of all, we want to find the range of D, right, or the phase shift. We want to know the smallest phase shift up to the maximum phase shift. We also want to know what the leakage inductance, L leak, or it doesn't have to be leakage, but the inductance that we're using in this converter. We want to know how big this should be in order to provide the necessary power. We also want to know what the output capacitance is, C out, and we also want to know what the turns ratio of the transformer is, if we have one. It's not always required. So this is what we want to find. Let's just redraw the DAB so that it's easier to explain what's going on. So this is basically what we have, right? We have our input voltage, our 4 primary side switches, Q1 to Q4, our leakage inductance, or the inductance, you could say, the transformer turns ratio, the secondary side switches, QA to QD, the output capacitor, and the load resistance. So what we're selecting is this, and then also the phase shift between these, which maybe I'll just indicate with this. So often with problems like this, the question is, where do we start? Well, I'm going to suggest that we start with this. We want to determine the turns ratio first, and then from there, we'll figure out the other stuff. So first, it might be good to recall some equations that we have derived from the previous lessons regarding the DAB. So we came up with the conversion ratio, V out over VG, and this is equal to R load D times 1 minus D over 2 FSW LLN, right? And D is really just related to the phase shift, right? D is simply the phase shift phi over TS over 2. We also have the output power, an expression for the output power, which is simply V out times VG, D times 1 minus D, over the same thing, 2 FSW, L leakage N. And we can also, derive the output current, equation for the output current, which is simply P out divided by V out, so it's VG, D, 1 minus D, 2 times the switching frequency, the leakage inductance, right? We already know this, and this is also equal to V out over R load. Great, so how do we determine n? How do we choose n? Well, what I'm going to suggest is that we look at the inductor current to determine what we should use. First of all, this application has a fixed input voltage. And output. Fixed input and output voltage. This is kind of important because it means that we don't have to design it for varying conditions. Really, we're just varying the load current. So because of that, because they're fixed, let's look at how the inductor current varies with n. And the inductor current that we've been drawing so far looks something like this, right? So there are four slopes here. Really 2 slopes, and 2 of them are inverted. But over here we have Vg plus V out over N all over L. Here we have Vg minus V out over N all over L. Right? So, well, here we kind of have an equation with n in it, right? So as we vary n, we can vary the slopes of these this inductor current, right? So for this case, the case that I've drawn, we've assumed basically that Vg is greater than V out over N, right? Because the slope is still positive. So Vg minus V out over N is still a positive number. However, we could choose another condition, right? For instance, we could choose a situation where maybe the Vg is less than V out over N, and maybe the current would look something like this, right? So again, we still have the slope Vg minus V out over N all over L, but in this case, Vg is less than V out over N. Right, so we've kind of seen 2 extremes, right? The middle case, I'll use a different color. The middle case is actually kind of interesting. This is what I want to highlight. So maybe case 3, the case when Vg is equal to V out over N. And what happens in this case? Well, let's draw it out. So if Vg is equal to V out over N, then this slope, Vg minus V out over N over L, is 0. So if we choose N such that this is satisfied, then we have 0 slope here, we have 0 slope here, and then clearly they're just connected. Something like this. So it looks more like a perfect trapezoidal waveform, you could say. Right? And this is the case that I want to use. Why? Why would we want to choose N such that this happens? Well, basically, the hand-wavy answer is that this wave shape reduces the RMS current. Or you could say that the peak is much closer to, let's say, the rectified average. Or the peak current is smallest. So by choosing N equals V out over Vg, we reduce the peak current in the inductor over the range of currents. And if we do that, then we can kind of reduce conduction loss a little bit. So what I suggest for fixed input and output voltages is N equals V out over Vg. You select N to basically be the ideal conversion ratio that you want. And then you simply regulate the the output current by varying D. So this is what I'm going to suggest, and this is kind of like the easy answer. It's going to vary if V out or VG varies. If your design requires that a wide range of input voltage or a wide range of output voltages, then you might have to choose something a little bit different. And maybe we'll look at that in a little bit. Let's write out some equations. We have N, but we still need to find D. So C out we'll look at later. These two are related to power flow. So we kind of need to solve for both of them at the same time. So this is like really range of D, right? So we have two limits on our current, right? So again, I out varies from 10 amps or from 1 amp to 10 amps, right? And we also have this equation. So we're going to have some D, I'll call it D2 for the 10 amp case, and we're going to have another D, I'll call it D1 for the 1 amp case, right? So we have this range of D. So let's just write this out. We know that I out is equal to VG D1 minus D over 2L FSN. We've determined N, and we have Fs given. So really we have two equations, right? One for minimum current and one for maximum current. So for the minimum current case, we have 1 amp is equal to VG, 48 volts, times, I'll call this D1, 1 minus D1, over 2 L leakage, another thing we're looking for, the switching frequency, 200 kilohertz, and N, which I'll just leave as N for now. The other case is the 10 amp case. And it's similar, right? 48 volts, this time D2 and 1 minus D2, all over the same stuff, right? So here we kind of have, we have two equations and three unknowns, right? So we're kind of stuck here a little bit, and we have to do some thinking to get ourselves out of it. So if you recall this equation, or if you consider this D times 1 minus D, if you think about the plot of this, I'll just say this is D1 minus D over D. This is a parabola, right? It's a parabola that points down. It has a maximum at D equals 0.5, right? So when D equals 0.5, this equals 0.25. So we kind of have an upper limit for how much power we can transfer, right? The most power we can transfer occurs when D equals 0.5. In other words, this is like the best, the phase for maximum power transfer. This is the D for maximum power transfer. Let's just write this out. At maximum load, we should choose D2, right, at the maximum current, close to D equals 0.5, right? Because that's when we're going to be able to transfer the maximum power. However, we will not choose D equals 0.5 exactly. We want a little bit of room. Why? Okay, well, there's kind of two reasons. One, we may need a little room for transients. In other words, maybe we want to increase the power transfer for a short period of time above our conventional steady state so that we recover in a quick amount of time. 2, the control action kind of flips at d equals 0.5. What do I mean by this? I mean, when we're operating from 0 to 0.5, d equals 0 to 0.5, as you increase d, the output power will increase. However, when you get beyond d equals 0.5, as you increase d, the output power actually drops. So what does that mean? It means that your controller may be telling your system to increase the power, but the opposite effect happens. So there might be some control issues if you do that. So we want to avoid this. So, somewhat arbitrarily, let's choose d equals 0.4. So d2. So at maximum power transfer, when we're sending our maximum current, we're going to set our phase shift, or our d2, to be 0.4. So we've eliminated one of these unknowns. We know that the peak d is going to be 0.4, and now let's find the minimum d. So this is actually pretty simple to do. We have 2 equations and 2 unknowns, right? We can pretty much just divide these 2 things to cancel everything out, right? So if we divide, let's say, equation 1 and equation 2, well, simply what we get is that 1 amp over 10 amps is equal to 48 d1, 1 minus d1, over 2L, L, 200K, N. And this is going to be all over pretty much the same thing. 48, this time d2, 1 minus d2, all over this same denominator. 2L, leakage, 200K, N. And we can start canceling stuff out, right? So we can cancel out this, all this stuff, right? And then what we end up getting is that we have 1 over 10 is equal to d1, 1 minus d1, and then d2 is just 0.4, right? So 0.4 over 0.6. And then from this we can find d1. And d1, there are 2 options because it's quadratic. However, one of them is going to be greater than 1, which is not, or greater than 0.5, which is what we don't want. We want the one in the range from 0 to 0.5, and it turns out that this is 0.24. Okay, so we have d1, and then we also have to find L. So let's find L. It's pretty much the same thing, right? We just have to plug in the correct equation. So let's just choose the 10 amp case, right? So 10 amps is equal to 48 volts. d2, 1 minus d2, this is, right, 0.4 and 0.6 over 2LL, 200K, and if we rearrange, we get LL, the leakage inductance, is equal to, well, I just solved for it, and it ends up being 27.65 microhenries. Right, so we've kind of determined most of the stuff, right? L, D, and N. Now the question is, what is V out? Or C out? How do we find C out? Well, this is actually kind of a challenging problem. Thankfully, by selecting N to be equal to V out over Vg, it kind of simplifies this analysis. So to do this, right, we basically have to inspect the output current, or the inductor current, right? So let's do that. So given we've selected N to be V out over Vg, our IL looks like the following. Right, so it's flat over here, we have our slope here, we have our slope here, and it's flat in this region. Right, so we have some peak current, I'll call it I peak, We know the slope here in this region is Vg plus V out over N over L, right? And it's the same thing over here. So our output current is simply the scaled rectified version of this, right? It's scaled by the turns ratio and rectified. So I out of T is going to be positive in this region, right? So from this period to this period, QA and QD are on, right? So IL and I out are going to match up. And then in the other region, they're going to be inverted, right? So drawing that out, it's going to look something like this, right? And then it's rectified, so we have this kind of waveform, right? And we know what the peak is, right? So the peak is simply I peak over N. Right, so this is like the time variant. This is the rectified current going to the output capacitor. We also know that the output current is some constant value, right? Somewhere here. Right, this is I out. And typically, to size the output cap, usually what we do is we find the charge, and we say that C out is equal to the charge over 2 delta V out, right? So this is what we've decided from the problem, right? The problem says 2 delta V out is 100 millivolts. So basically, we just have to find the Q that we inject into the output cap and divide it by that voltage to determine what the capacitor should be. So what is this Q? It's simply the difference between the output current and the current that you're sending to the cap. In other words, Q is exactly this, right? So this is like the positive Q and this is like the negative Q. By CCB, these two Qs are equal. So all we have to do is calculate this Q and divide it by 2V out and it gives us C. And to calculate this, there are two components, right? So we kind of have this square over here, which is easy to calculate. I'll call that delta Q1. And then we also have this triangle, right? Which is also easy to calculate, right? And I'll call this delta Q2. So we can write out expressions for both delta Q1 and delta Q2. Right? Delta Q1 is simply equal to this time difference times the height, right? Which is simply I peak over N minus I out, that's the height. And the time is simply Ts over 2 minus phi, right? We know what phi is, we know what Ts over 2 is. For delta Q2, it's the area of a triangle, so we have half the base. In this case, the base is, well, it's a similar triangle. So really you could calculate the area of this whole triangle and then multiply it by the square of the ratio of the side lengths. In short, what we end up getting is half the base. So we calculate the area of this whole triangle, which is half phi over 2 times I peak over N, right? So that's the area of this entire triangle here. And then we multiply it by the square of I peak over N minus I out, right? This height, over I peak over N. And that's all squared. Okay, so let's simplify this stuff. Let's figure out what delta Q1 and delta Q2 are. So simply subbing in the variables we know, we have delta Q1 is equal to Vg dTs over 2Ln minus Vg d 1 minus d over 2L Ln. There's a Ts in here. Times the time difference, right? So this is simply I peak, and this is I out. And then we have Ts over 2 minus d times Ts over 2, right? Phi is simply d times Ts over 2. So there's a lot of common terms. We can factor them out. So let's do that. We have Vg dTs over 2 Lln times 1, right? Because we factored out this whole thing, minus 1 minus d And then we can factor out a Ts over 2. So Ts over 2, 1 minus d. Simplifying again, this is d. We have a Ts over 2, so let's just group it all together. So we have Vg, d squared, Ts squared, 1 minus d, all over 4L, LL times N. Cool. All right, so that's delta Q1. And so to be clear, I derived this from I peak. So I peak is simply equal to well, going from minus I peak to I peak, or from 0 to I peak, is simply Vg plus V out over N all over L times half of phi, right? Which is dTs over 4. Note, because we selected Vn to be V out over Vg, this is equal to Vg, so we have 2Vg over here, and then I peak, again, because of the specific choice of n, we end up getting Vg dTs over 2LLn. So, in the end, this is delta Q1. Now let's find delta Q2. Well, it's pretty similar, right? So we have I peak over n minus I out, which is exactly this thing. So I'll just write this again. All over I peak over n. And this whole thing is squared. And then we have half phi over 2, which is, again, dTs over 4, times I peak, right? Which is Vg dTs over 2LLn. So we can cancel a whole bunch of stuff here, right? So we can cancel this out, this, and then that common term is also in here. So what we end up getting is 1 minus d all over 1, and this is squared. And then we have Vg d squared Ts squared all over 16 LL times N. And this all simplifies to Vg d to the 4 Ts squared over 16 LL times N. So these are our two pieces, right? And then finally, to find the total delta Q, it's simply delta Q1 plus delta Q2. So this is equal to Vg d squared Ts squared times 1 minus d all over 4 LLn plus this piece, the second piece. And if you want, we can factor this because factoring is nice, right? So we can factor out a huge chunk. And we get 1 minus d here plus d squared over 4. So this is our delta Q, right, for C out. So the question becomes, what D do we choose? To size C out, what D, or load current, do we choose? Right? What we want is that the output voltage ripple is at most 100 millivolts from peak to peak at all conditions, right? So we want to find the case when delta Q is the biggest. Right? If delta Q is max, then the C we choose to contain that delta Q will be large enough to ensure that delta V is smaller for all other cases. Well, how do we find the max Q? Well, D is a variable. D is our variable in this case. So the max Q, so all we have to do is differentiate this delta Q by D, right? And then we set that equal to 0 to find the mins or maxes, right? So if we do this, I'm simplifying. I'm going to toss this D squared in here. And then I'm going to differentiate, right? This first term doesn't matter because we're going to equate this whole thing to 0. So in the end, the derivative is going to be 2D minus 3D squared plus D cubed. And that we're setting equal to 0 to find the minimum. So we immediately have one solution, right? D equals 0. So D equals 0 is a solution to this problem. That is either a minimum or a maximum. And then we have two other roots, right? So you can simply factor this. It turns out the other solutions are 1 and 2. 2 does not work, right? Our range of D is limited from 0 to 1. To the second derivative, right? So we can look at the second derivative with respect to D, and that's equal to 2 minus 6D plus 3D squared. And if we evaluate this at D equals 1, it's positive. Or it's negative, right? At D equals 1, which means that it is a max. At D equals 0, if we evaluate this at D equals 0, it's actually positive, right? Which means it's a min. This means that the worst case, the largest Q, is going to happen when D is maximum, at our maximum power. And that kind of makes sense. So for this particular case, it's not always the case. For this particular case, we size C out at D max. In this case, our D max is 0.4, right? We decided that beforehand. So we're going to choose D equals 0.4. We're going to plug it in here to find C out. So therefore, C out is going to be equal to delta Q evaluated at D equals 0.4 over 2 delta V out. So let's do that. What do we have? We have VG 0.4 squared TS squared all over 4 LLN times 1 minus D, or I'll just put in the 0.6, 0.6 plus 0.4 squared over 4. And solving this, it gives you an answer of 109.2 microfarad. So obviously you can't find an actual cap with this value, but this is telling you the minimum it needs to be to constrain your output voltage to this value. And to be clear, there's actually 2 times 50 millivolts in here from the specification. So this is the C you need. Typically, we actually don't size C based on the ripple requirement. Usually it's sized on the transient requirement. So what does that mean? Well, in short, instead of designing for ripple, usually converters will experience heavy to light or light to heavy load transients. So what happens in that case, you can imagine that we have some V out, right? And it's living its life, and then suddenly the output current jumps from one value to another, suddenly, right? The load demands some amount of current. The converter isn't actually able to respond instantaneously to these very sudden changes. So the output voltage for a short period of time, the current that you're providing doesn't match the load current, so the output voltage drops a little bit and then recovers to the value you desire, and this settling time, or this response time, which we'll call dt, is determined by your controller. So basically, how fast your controller is able to respond also determines how big your cap needs to be. But this delta V is usually what you're trying to control for. So you might know that your controller can only respond within, say, 20 microseconds or something. And the load current, the maximum change in load current might be from 1 amp to 10 amps, like in this example, for instance. Then you need to size C out such that this delta V, and it might not be 100 millivolts, is not exceeded during that load transient. But yeah, that's basically the last component. C out is the last component. However, there is more to think about with this. There is a lot more to think about. Right? This is like kind of the contrived answer. What happens if VG varies? Right? So instead of VG equal to 48 volts, what happens if it changes from, say, 24 volts to 48 volts? So this time, stuff is going to vary. And maybe what you could do for your specific design is come up with cases, right? So you could come up with the worst case, lowest VG, for instance, and then highest VG. Or you could assume that, say, all cases are possible within a single application. And maybe what you do is you say that I know that my load current can vary from one value to another, and I know that my input voltage, VG, can vary from one value to another. And then maybe what you could do is say, okay, well, it goes from 1 amp up to 10 amps, and the voltage goes from 24 up to 48. And maybe you could come up with like a probability or a percentage of time that the converter operates in these different conditions, right? So maybe this is like percent time that it stays in these different operating conditions. And maybe what you end up getting is some kind of heat map telling you how often this converter operates in the different conditions. Maybe it looks something like this, right? So you have some surface, right? And maybe you want to design for the case that you most often encounter, right? Some region where you spend the most time. That's where you might want to optimize your design to operate at its best because you're spending the most time there. And then you just have to ensure that the edge cases are taken care of. However, one important thing to think about is the fact that the total charge or the output capacitor the output capacitor design is going to vary because we don't have this special case where N is going to be V out over VG. Now, because VG varies and N doesn't vary, there's going to be cases where the current shape is going to look different depending on the voltage and current. So let's go back to our general current waveform. So if you recall, the general current waveform for IL looked something like this. Right? And then if we consider the output current, the rectified and scaled version of this, it might look something like this. And similarly, we would have our output current somewhere here. On this original current waveform, IL, on the primary side, we have I1 over here and I2 over here. The scaled versions would be I1 over N and I2 over N for the output, so we could say that maybe this is I2 over N and this is I1 over N. And then we have to determine the charge sent to the output. So we kind of have three regions here now. So, region 1, I'll call this delta Q2. We have another region down here. This is the rectangular region, which I'll call delta Q1. And then over here we have again a triangle, which I'll call delta Q3. And now the total charge that we have to determine is the sum of these three charges. So to help you out, I'm going to give some important equations relating these variables. So, on the one hand, we have delta Q1 is equal to I1 over N minus I out times Ts over 2 minus phi. So this is very similar to what we did before. Delta Q2, this triangular region, is equal to 1/2, it's a triangle, right? So I2 over N minus I1 over N times Ts over 2 minus phi, half the base times height. And then finally, delta Q3 is kind of similar. Here I used a slightly different approach to doing it. You can calculate this time, which I'll call Tx, and then we have that delta Q3 is just half Tx times the height, which is I2 over N minus I out. Okay, so we have these extra variables. So we have I2, I1, Tx, so let's solve for what they are. And I'll just give it to you because deriving it is going to take some time. So first of all, I2 is equal to Vg minus V out over N times 1 minus 2d all over 4L Fs. I1 is equal to 1 over 2L Fs times Vg plus V out over N times d minus Vg over 2 plus V out over 2N times 1 minus 2d. And we have Tx is equal to I out over Vg plus V out over N times L leakage. Okay, so these are kind of like intermediate things that we can use to solve for delta Qs. Let's keep going. So first, I want to determine this I1 minus I out over N. So I1 over N minus I out, sorry. This term is going to be equal to Vg times 1 minus 2 d prime plus V out over N. And I highly suggest that you derive these yourself. It's a good exercise. And this is all over 4L Fs N. I also want to know I2 over N minus I out. This is equal to Vg 1 minus 2 d prime minus V out over N times 1 minus 2d. And that's all over 4L Fs times N. And then finally, we have one more term that we're kind of interested in. It's this I2 minus I1, right? So I2 over N minus I1 over N. This is equal to 1 minus d Vg minus V out over N over 2 Fs LL N. Delta Q is simply delta Q1 plus delta Q2 plus delta Q3. And again, just writing it out because going through every single step is going to be torture. What we have is that delta Q is equal to d prime over 8L Fs squared over n times Vg 1 minus 2d d prime plus V out over n plus, so this is like the first term from delta cube 1, d prime squared 8L Fs squared over n times Vg minus V out over n. This is like delta Q2, and then delta Q3 is d prime over 16L Fs squared n times Vg 1 minus 2d d prime plus V out over n times Vg all over Vg plus V out over n. So this is the final equation for delta Q. And again, we kind of have to do the same thing. We have to determine the worst case Vg, or the worst case delta Q. So here I out and Vg are kind of independent. And you can kind of see from both these terms that Vg is in the numerator for both of these, and then this smaller term has Vg in the denominator and the numerator. But in the end, there's Vg squared over Vg. In the end, this increases with Vg. And increases with D. So we're going to choose the max D and the max Vg again. So 48 volts and when D equals 0.4. Because we're still going to choose that our maximum power transfer occurs for some maximum D, which is slightly less than 0.5. We might also say choose N in the midpoint of Vg. Right, so maybe N equals V out over Vg when Vg is equal to, say, 36 volts, right in the middle. And then that way, maybe for over the full operating range, the current peaks don't get too high. Maybe that would be a choice you would make. And if we do this, we can maybe say that we can choose L, right? So maybe L for this particular case, in this case 5 over 36, we could say L is equal to Vg d times 1 minus d, or d prime, 2Fs I out n, and we evaluate this when n equals 5 over 36, d equals 0.4, and we want to choose the worst case Vg. And in this case, the worst case Vg, when we send, we have to choose L so we can send the amount of power we want across all cases. When Vg is high, think about P out, right? So when Vg is high, if Vg is high, then we can send more power, right? Because it's proportional in this equation, right? As Vg increases, P out increases, which means that L doesn't have to be that big. However, when Vg is smaller, we need to be able to send more power. To do that, if we're designing L, if we want to send more power for a fixed frequency and a maximum D, we have to make L smaller. So the worst case for sending power, which is kind of what L controls, is when Vg is minimum. Right? Imagine if you chose the L when Vg was maximum. The output is drawing 10 amps from the converter. We choose D at this maximum power transfer to be 0.4, right? And let's just say Vg equals 48 in this case. Well, everything is set, right? So we're at our maximum D, V out doesn't change, Vg is 48 volts. L, the L we've chosen for this particular case is fixed, switching frequency is fixed, N is fixed. So we can send as much power as we want. However, as VG starts to decrease, we can't increase D anymore, right? D is already at the maximum value we've set, in this case 0.4. We can't make it go any higher, right? We're limited now. We're limited by L. We have to change something else. Maybe we have to say decrease FSW, but in this case we don't want to. So if we design it at VG equals 48 volts, we're not covered, in this case, at VG equals 24, right? We wouldn't be able to send the required power if VG decreased to 24 volts because the output power is proportional to the input voltage. So for that reason, we evaluate this when VG equals 24 volts. That's how we choose our L, right? So our L ends up being smaller, which allows us to send more power. And in this case, the L would be something like 10 microhenries. And again, I suggest that you choose this or you go through this yourself. In any case, that's kind of what I wanted to talk about. I mean, we could go further, but it's already been probably 40 or so minutes, maybe an hour. So hopefully this was helpful. And yeah, we'll do some more lectures, look more into resonant converters, and I hope this was helpful. Thanks.